Good morning, good afternoon, or right in the middle between the two of them. Welcome to another episode of Takeo Tuesday, everybody. Thanks for joining us after the holiday. The long weekend, the unofficial start of summer, even though it hasn't felt like that here in New York. I mean, on Long Island, we still have heat calls going on, you know, going out to turn the heat back on in some parts of the house.
It's like that in New Hampshire too, brother.
Yeah, I mean, I was joking with a contractor the other day, and he's saying, "Yeah, I'm going to have to call you up. I have some questions on a snowmelt system." So,
They got about 6 inches of snow. They got about 6 inches of snow on the top of Mount Washington here in New Hampshire over the weekend. That's how crazy it's been.
That's
I'd
crazy.
just be
Down in
bragging.
California.
I'd just be bragging if I
California,
told
Jason,
you
you have this problem.
I got a sunburn on my forehead yesterday.
Oh, I can't say it, but I have a few choice words for you.
Yeah, Paul's heat came on this morning also in New Jersey. Yeah, you got your thermostats all set up in auto mode and stuff. Yeah, the heat's kicking in. All depends on that differential that you could program between the heating temp and the cooling temp. Yep. So, or you just need the safety and security of making sure everybody's happy back at home. So anyways, thanks everybody for joining us again for another episode of, Takeo Tuesday. This is a residential training, but we're going to leave the basement and go into some of those mechanical rooms. We're looking at still with our ECM, but larger. Everything that we've talked about on the residential side of our classes here have been our smaller 00E series circulators. This series here, a little bit bigger for you. All right. For example, up to 320 gallons a minute. So I want to go over some of those larger projects because, heck, we do see these in houses. They're just very large. All right. It's not a basement, it's a mechanical room. You've got that 10,000 square foot starter castle. 2 people live in it, haven't seen the dog for days. All right. This is where you might be applying some of those circulators, some of those bigger snowmelt systems out there today. So this is what we call our VR series of circulators. So for those of you out there, everybody's microphone is muted. You have the ability to communicate with the 3 of us here, with John Barber and Jason Cox here. They both are listed as Takeo Comfort. When you look at the camera, so they haven't updated their names yet, but they will now that I just pointed it out.
That you brought it up.
So ask any questions that you have. This is going to be a 2-part series. We're going to go through applications today, and the part 2 is going to be on programming and advanced wiring on these things. So we're going to go through some of the basic programming today, and the next class is going to be some more of the advanced stuff out there. So anyways, let's get this thing started, shall we?
Real quick, Dave, if I could interject, just do me a favor before we get started, folks, just so you know how to ask the questions, just go to that question chat section and say hello or where you're from. That way we know you can hear us and you know how to do that. So we got a few folks already chimed in, but if the rest of you could do that for us, that way we know that you can hear us and we know that you know how to ask a question, and we'll be answering them as we go along. So
yes, and do not be afraid to ask any questions. I know I started to bring that up and I forgot when I saw the names on the screen. And also answer some questions as we go through this thing, because it just makes sure that we're still connected and that we're not just talking to the 3 of us here as we start talking about. So excellent. Thanks, Eric and Brian. Awesome. Tim. Good morning, Mr. Tim.
I think we should all rise that Tim Stingle is in the house.
Carter from Calgary. Excellent. All right. So let's talk about this VR circulator series here. All right. We do have it in 2 flavors. We do have our cast iron. We also have a stainless steel model for some of your open systems, which is also NSF rated, also NSF hot rated as well. All right. So when we take a look at this circulator, you could see here a couple of different profiles. I want to make sure that you see how this thing looks and what's going on with this circulator. So here you see the stainless steel that does have an insulation jacket around it. And then we have the stainless steel one here. So your cast iron, the first one cast iron with the insulation jacket, your stainless steel that does not. And you can also note, even if they are both get insulated on the job site and you can't tell which one is which, the one with the black face is going to be our cast iron. The one with the white face is going to be for our stainless steel circulators out there. But functionally, they are both the same here. All right, they're both the same in what we got going on. So what are some of the features that we have built into these circulators before I get into where we apply these things? So again, being variable speed, these are wet rotor circulators, and we also have that opportunity to change that programming. So we see here proportional pressure, PP, that's what the PP stands for here. We have 66 different settings, all right, and in setting these things up. Constant pressure, constant discharge pressure. We'll talk about those applications coming up. We also have where that proportion is up to a 50% incline or decline. You'll see on the pump curves a little bit. We do have a function in here called Taco Adapt. We can use it in a fixed speed mode as well. Now, when we start talking about some of our advanced controls, we can also have its speed controlled by 0 to 10 volts or through a pulse width modulation. We do have the capabilities of Modbus and BACnet with this circulator as well. We can also do a twin pump mode, all right, where we can do a lead lag operation and we can do standby and make these things run in parallel. All right, so we've got that functionality built into the power heads as well. And we do have a function called night setback, and I want to make sure I go into details with that a little bit different than what you think about. Now, we also have a whole ton of protections built into this thing too, depending upon your applications, your job sites that you're working at. So you can see here, we have a dry run protection and overcurrent. So a lot of these things are going to help save the circulator. You will have an error code pop up on the front side of it here to make sure it doesn't get burnt out on the job site. All right, so you'll see all these things that could pop up with that error code, and it does have that whole section in the installation manual that goes through some of those different error codes that may occur out there on the job site itself. So I have also included today under the attachments, you're going to see the catalog sheet as well as the instruction manual for this circulator itself. All right, so let's take a look at what some of these performances are. So the VR15 series, we have an L, M, and H series. This is not just the same circulator, just detuned from the 15H. All right, they are different circulators. All right, and we're looking to go from 120 gallons a minute up to about 50 foot ahead with the 15 series, and we have these 3 different series to match into your flow and head. And we've talked about flow and head calculations and make the circulator fit the one that fits the best to your application. If you've got a system out there and it's well below the 15L line, you don't necessarily want to put the 15H and just tune it all the way down. So that's where we came up with these 3 different models to fit into different applications. Then we jump into the VR20. All right, VR20 getting a little bit higher out there in the gallons per minute. We got the 25, which we're approaching that 300 gallons, looking at about 275, 280 or so gallons a minute, up to about 65, 60 foot ahead or so. And then we've got all the way up to the VR30, hits the top end at 320 gallons a minute and about 65 foot ahead. So we've got a very wide range of circulators here. Now, these are true whether it's going to be cast iron or stainless steel that we see out there. Now, just to have a quick inkling on the naming process that we have where we come up with the 15, 20, 25, and 30. So we've had this circulator out or variation of it over the last 15 or some odd years. And they originally designed the VR15 was meant for 1.5-inch pipe for that flow profile of 1.5-inch. And then the VR30, meaning you're going to look at 3-inch pipe for your systems. So that's where that naming system started from, just so you have a little bit of an indication. All right. Now, what you're going to see on the faceplate here is that we've got some interface in order to do some of the program, but it also gives you some of the data when this circulator is up and running. So you can see the power consumption in kilowatts, and it will rotate every couple of seconds through each one of these settings. So you'll see kilowatts, all right? You'll see the pressure drop, the estimated pressure drop that the circulator is operating in. What is that foot of headline, all right, curve that we would be looking at? You can see your gallons per minute flow. Again, it's an estimate. We don't have a flow meter in there, but it is a calculation that we have a plus or minus built into it. And you can see the estimated RPM. All right. I mean, not estimated, but you can also see the RPM, the speed of this circulator in what it's running at. Over on the left-hand side, you're going to see this bar graph, so to speak, and this is going to give you a quick idea of the approximate speed of the circulator. So I've had this question a few times before, and they see the 5 lights and they say, well, it's running speed 4. The speed, that light 4 has a range of speeds that it's operating in. So it's just so you have a quick reference to see what it's operating at. On the right-hand side, you're going to see what mode the circulator is going to be set up in, whether you're in the take-o-adapt mode, you're looking at proportional pressure, constant pressure, fixed speed, and then there's the night mode, and we have a couple of buttons here on the front side that you can program through the faceplate here. So the operating modes that we have, all right, that fixed speed mode is now going to be, it's not a variable speed, it's only variable speed when you change that speed. So when you go ahead and change it and set it, it stays that speed continuously. We're going to use that in, say, a zone pump application. Then we have our constant pressure mode, and that is going to be used in, say, a zone valve mode or a control valve, open close valves, nothing modulating, just going to be an open close. In this mode, we are going to see a variable speed portion of it where the circulator will speed up and down as those automatic valves open and close. All right. So you'll see that by that icon here on the right-hand side, right in the middle at that 3 o'clock position. Now you'll see proportional pressure. Now proportional pressure is when you have something that is like a thermostatic radiator valve, something that is a proportional valve, never goes fully open, never goes fully closed, always has some sort of modulation. Now, there are applications out there that you might see an open close valve, but we might want it to operate in proportional pressure, and we'll show you those applications as we reach that. Then there is the auto mode, all right? And the auto mode is what we call take-o-adapt. This is the default mode of the circulator. Again, we're looking at something that has some modulation to it in those valves. So it's not, just put it into the take-o-adapt mode and it's going to figure it out for you. It has to hit certain criteria that we're going to hit as we go through there. And then there's the night setback. All right. And the night setback, I want to make sure that we understand what this is going to get for you, because this circulator is also designed to work on both sides of the pond. All right. So it is not just necessarily designed for our North American installations. It is also designed for our European installations as well. And the night setback is different than what we do here in North America for setback. Most of our setback that we are going to do, whether it's going to be in a residential setting or even commercial settings, is we are setting back the air temperature in the space that we are delivering that heat to. All right, that's how we typically do a setback. The setback that is built into the circulator is looking at water temperature. If it sees a temperature drop over a time period here, over a quick time period, not slow like over the course of an evening or during the daytime, it will operate in its lowest speed. So because now we're looking at the boiler or the heating equipment that is doing that setback and lowering the water temperature. So if you have a system that is doing that, you're dropping the water temperature when the building and the house is unoccupied, then you can use the night setback function. But most of the time we're doing an air function. So if anybody out there has done any night setbacks with water temperature, let me know. Curious as to how it was achieved and how you set it up out there. Give us a quick shout out there, because most of the time my experience has always been air. If you've done a water setback, please let me know out there. It'd be greatly greatly appreciated as I do more and more training classes with this circulator series itself. I'd love to know those applications and why you went that route. Anyways, let's talk about some fixed speed applications that we have out there. Fixed speed applications where the circulator is designed to be set up and run that same speed and not change. All right, and we're looking at a couple things. So what I want to show you first off is taking a look at the performance curves of the circulator itself. You'll see here that it's got a minimum speed, it's got a maximum speed. All right, and what we do is program all of these individual curves into the circulator itself. All right. So what we're going to do is basically choose which one of them we needed to operate. So here you do need to know your flow and head. All right. We have to have that math that we've talked about over the years, making sure you choose the proper speed that the circulator is going to run at. So it doesn't always want to run at full speed. You might sign it and hey, that's going to probably be 1 out of 100 applications where you might get the exact speed when this thing's running full speed out of the box. That's what you need for the application. All right. So what you have here is obviously, as we talked about, your system curve is going to be based upon your design point. All right. And then you choose the curve that it's going to operate on. Again, if it was the main point all the way out there, you make it run full speed. Here you see you're about 60% speed of the circulator. So again, knowing what it needs to. Now, when you program it, for example, if this was your design point, it's going to operate on this curve. All right. Now it's not going to flow all the way out here or down here on that curve. It's going to operate on this point because that system curve is that unique hydronic fingerprint that you're doing. All right. So, and it's going to run right there and stay there always because this never changes. This system curve, because you don't have any open closed valves going on, it's just going to be that steady flow and steady RPM continuously. All right. So we have that. So that's how you're going to set this up. You need to know which one of those curves we're going to operate on. All right. So a zone pump application. The way it's going to look is exactly simply as this. All right, you may have one, you may have multiple circulators. They might be zones and they all have their own standalone circulator where nothing changes the pressure from one circulator, one loop to the other. All right, there's no open close valves that are going to open and close. There's no control valves. There's no TRVs. There's no nothing. A signal comes in, tells that pump to run, and bang, it goes. All right. It gives you the same flow in September as it does in January. All right. There is no reason for this thing to change speeds at all. So you program it for that application. These could all be 3 different speeds that they're set for because of the loads that they're connected to, but they will never change. All right. And we've had this conversation before, whether you like to zone by pumps or zone by zone valves. That's your personal preference. All right. In sizing up the system, maybe it's a better fit for this application rather than having one monster pump out there. You might have several smaller circulators out there, like 3 VR15s on one application. So here we may also see, and here's the beauty of these circulators, that we can do a little bit of both in the same project. This one here, this heating circulator up at the top of this piping diagram, is going to be set up for an open closed valve system. All right, so this one is not going to be in the zone pumping application, but this one down here will be. All right, which is maybe going to a large indirect tank to get us our hot water. All right, or several tanks where we're going to be charging up those tanks for the day. All right, and what we have is a set flow that these tanks need to see and a set head loss. So this circulator does not ever need to change speeds here. All right, but this one, we do want it to change speeds, and we'll talk about programming and setting up in a little bit. All right, again, now maybe getting away from different boilers. Now we're looking at some wall hung. We could have a series of wall hung circulators, wall hung boilers out there. And again, this is where we talked about our zone pumping, just like before. Didn't matter what the boiler was, but depending upon the size of your circulator, we might see one of these here. It might not be an internal circuit, may be an external circulator. This is going to be a fixed speed setup. All right, so we'll have fixed speed going out to the zones, but my boiler may also be a fixed speed. Okay, So, and we'll talk about some of this boiler circulator as becoming variable speed, but we'll do that in part 2. All right, so how do we set this up from the faceplate? I'm doing some of the basic programming. Part 2 is going to be some more of the advanced programming and setups on these things. So programming here is all done via the faceplate here. All right, so in order to set up your fixed speed settings, we have an adjustment speed between 1100 and 4400. So 1100 being our slowest, 4400 all the way up to our highest. And we have 100 RPM increments as we go through those settings. So in order to program and start setting this up, like I said, the default of this circ, as soon as you put power to it, it's going to be in the auto mode. All right, that take or adapt mode that we have. So what we're doing is we're going to hold down the set button for 3 seconds until the mode light is flashing. And it would start off as the A would be flashing here. You hit the up arrow until you get to the mode that you want this circulator to operate in. We want to do fixed speed right now, so we're going to use this bottom left hand, bottom right hand icon, which is my fixed speed. Once that is flashing, hit set. Okay. Once we hit set, then it's going to ask you what RPM you want it to operate at. And then you're going to hit the up or down arrow, all right, between, again, 1100 and 4400. So it would be a good idea to know what flow and head you want the system at, plot it on the performance curve based upon which circulator you have, whether it's the 15 all the way up to the 30, and then you're going to get an idea of that percentage. So we're not programming in the gallons per minute. And if you're not sure where it's supposed to line up on the curves, or that system curve, but you do know the flow, what you can do here is just come along. You're going to have to select an RPM, hit set again. All right. When you hit set, then you lock it in there, let the circulator start running for a little bit, and then verify the gallons per minute that it's going to show you and that it's close. So we're not, like I said, we're not setting gallons per minute. We can only view it. You're going to be able to set the RPMs that hopefully get you close to there. So if you're looking for an exact, you might have to play around back and forth a little bit going into this programming in order to get the correct gallons per minute and RPM to match up together. Does that make sense? I just want to make sure that everybody's familiar with that. And what I have found a couple of times with this circulator when programming it, this is probably the easiest setup that we have. We've had people not hit that last set again, and it was just in that default of, like, say 3,800 RPM, and they could never get it to run maximum. A few guys were trying to get it to run maximum just for purging purposes. They were setting up that and just getting things moving for the first time, and they kept on hitting that last set because they would see the RPMs. They say, okay, 44, it would be 4.4, and they'd walk away. And without hitting any buttons, it will automatically just go back to what you left it at or what you started with as an RPM. So just remember to hit that last set again. Okay. Excellent. All right. Let's get into our any questions out there, John?
Nothing yet there, Dave. Nothing yet there, Dave. But Tim Stingle did say that he misses us too.
Okay.
So that's good. That's good. And folks, any questions you have, is please type them in. We'll monitor them on our end, and we will gladly interrupt Dave anytime we need to. So type them in once you get them.
Yep. In 23, less than 23 hours, about just less than 24 hours time, you will get a link to this recording. You'll also get a link of your PDH credit that you attended the class. If you are watching this after the fact and you did not get to watch it live, unfortunately, you will not get that PDH credit that we have out there, but you will still be able to. If you can't make the classes, still register, so this way you can still get the link to the videos. Anyways, excellent, everybody. Let's take a look at constant pressure applications. What are we looking at for constant discharge pressure? Now this is becoming a variable speed circulator, so the circulator will automatically respond to the valves opening and closing. So what we're looking at again is that same pre-programmed curves. All right, so the curves of the curves of the curves. We can't get anything away from that. But what we do is we put a maximum on how much higher it can go or can back up the pump curve itself. And we want to maintain a constant discharge pressure. By doing that, we quiet the system down. We eliminate the needs for pressure differential bypass valves or any type of bypass valve for that matter. All right, the system quiets down as the valves close down, and then the circulator slows down as well. So this might be your entire system all running, all valves open, all right, and you'll find that system curve follow out. But what happens is, since it has to operate on the curve, if a valve closes, all right, it's still trying to stay on the curve, and then it realizes that it's going above the pressure that we have it programmed into. So you'll see this little bit of sawtooth function. If you were to watch it live, you'll see this sawtooth. It'll go up and say, nope, I need to come back down. Let me get back down to this proper RPMs here, all right, and maintain that constant discharge pressure. So it will slow down as your valves start to close down and automatically choosing a different curve. So if it was all zones running and we were way out here, out there, we're running 4,400 RPM and we're coming all the way down to this one. So probably about half of that speed of the curves that you had available. But every time a valve opens and closes, the circulator will slow down or speed up there, but maintain that constant discharge. Sizing here, you find the gallons per minute for every zone. You also need to do the head loss calculation of every zone or loop that you have in the system as well. And then you don't add up all the head, you find the highest, all right? So this way, if you can satisfy, say, 15 foot ahead, I can satisfy everybody else that's less than that. But the gallons become cumulative, so you need to make sure you add up all the GPMs. So when we're looking at zone valves or a open close valve, all right, a control valve here, in this application, yes, the circulator can be programmed in that setting here. We'll make this variable speed as these valves are opening and closing. In this application, again, we're looking at fixed speed. All right, so nothing to change here. There's no flow characteristics that are going to change through the boiler itself. We're going to make sure that stays in a fixed speed application. All right, we might look at an application like this. All right, a lot of home runs, maybe some sort of manifold or a header, and you could see actuators like this. So this could be, say, a PEX system, radiant floor heating, panel rads, lots of different designs out there on what you got going on out there. But again, actuators on a manifold or on a header is a zone valve. It's going to open and close. They're not modulating. There may be slow opening, but they're going to go full open or they're going to be full closed. We would also want this to be in a constant discharge pressure as well. Okay, so that's what we're looking here. All right, this circulator again going to be fixed speed.
Dave, we have an interesting question here. If I can, from Richard Nestor. How does the pump know when to speed up or slow down as valves open and close? Is it pressure loss or flow? It's
PFM.
a good question. That's a good question,
yes,
isn't it?
It is. I love this question. This is what I like to call PFM. It's pure effing magic inside the circulators.
No, it's not. No, it's not.
I'm kidding. I am kidding out there. All right. So how do the circulators know to speed up and down? Well, there's no pressure sensors built in. All right. It doesn't know anything really about what the water's going on. All right. What it does know is an RPM and an amp draw. All right. It knows those two things that are happening inside the circulator itself. And so what it's going to do is look to maintain a certain amp draw and RPM correlation to each other. So for example, if I had two valves that were wide open and the circulator is running, what it wants to do is try to push as much water as it can into each one of the pipes in front of it. That's it. It is going to jam as much water as possible into each loop. All right. So then it's going to find its nice happy point right there. So now imagine one of those valves closing. And as the circulator found its happy point, what happens to the amp draw of the circulator at this point? All right. So I've got steady speed as if it was two zones were open. Now one zone closed. what happens to the amp draw of the circulator there? All right. So type that in there real quick. What do you think happens with the amp draw on the circulator itself? All right. Richard answered right away.
We got an increases.
All
We
right.
got a goes up.
Goes up. All right. Those are two very good answers.
And everybody else is just watching. Nope. We got increase.
Okay.
We got goes up.
Goes up. Goes
We
up.
got a no go. We got no go downs us.
No
we,
downs. Yeah.
We have a consensus here amongst those who have answered that it goes up, that the amp draw will go up as a zone closes.
All right. And unfortunately, it goes down. And I was with you guys all at the same time that I all thought, at first when we started introducing our variable speed circs and understanding the mechanics and the software inside, I was thinking it would go up too because, hey, man, it had all this water that it was trying to push. All right. And now I got to try and take all of this water and jam it into one hole. And that's actually the opposite of what happens. What happens is the amount of water that the circulator was able to see dropped. So it says, oh, my amp draw is going to go down. I can't push as much water any longer. So now I'm going to slow down. All right. So my amp draw goes down. So therefore my RPMs are going to go down, and then it finds a new happy spot. So only one open, one closed, finds a new happy spot, making sure I can satisfy this one going. Now imagine the valve that's closed and it opens. Now we start thinking about, why does the amp draw go up? Because it just said, wow, I have all this more water I can pump out now. I have a lot more work to do. So my amp draw is going to go up. So I need to speed up, making sure I can satisfy both of them. Now, again, remember, this will be the same flow in September as it is in January. All right. It doesn't know anything different. It just sees, hey, I'm going to shove as much water as I can into the hole as possible. So that's what's happening here. This is what we consider a delta P function in the circulator itself, a pressure differential. All right, it's not reading pressure; it's looking at an amp draw and RPM. So excellent question, Richard. Thank you for bringing that up. I forgot to set that up on the slide here, but I knew somebody would ask it.
Ahmed asked this question or made a statement earlier. Remember, we have constant pressure and proportional pressure. Ahmed had mentioned that when the RPM is decreased subsequently, the pump head will be decreased, and we can make sure that at the low demand, the water could actually reach the index unit. Now, I think I understand what he's saying. In proportional pressure setting, that is true. As flow goes down, the head pressure differential created by the circulator goes down. But in a constant pressure mode, we don't do that. We actually keep the pressure differential that the circulator creates constant, just slow the pump down to maintain that pressure differential.
Right. So when you see a system like this here with these zone valves, all right, when we reach up to the zone valves here, this is obviously a fixed length to each one of these valves. And then the head loss is going to come from after this header going out to each terminal unit. All right, so that's where we want to make sure this is running in a constant discharge pressure. I've got an example coming up that's going to show you open closed valves that we will want it to operate in a proportional pressure, but you got to make sure the piping layout supports it. Okay, so this is going to be your open closed proportional constant discharge pressure here. Perfect, because of the distance between the circulator and the valves is consistent, and of course really consistent with this one since they are this far apart from each other. All right, now programming here, all right, is not looking at an RPM, but what we are going to do is program in half-foot increments. Now, I don't have a minimum because each one of these circulators is different. All right, so out of the 12 different models that we have, each one of these are going to be a little bit different in your half-foot increments on what the minimum is and what the maximum is going to be. So I just figured I'd give you a nice general overview. Again, we all start off with hitting that set button. All right, hold that down for 3 seconds. Make sure we get to the icon at the 3 o'clock position with that line on there. So this is showing like your head and flow curve and that constant discharge pressure. All right, then we go ahead and choose, once you hit set, all right, make sure the light becomes solid. Then it's going to be your foot increments. And so in every half a foot, You program it to what your maximum is going to be. All right. And then, and I didn't put it here, one last thing that has to be here, and I did it on purpose to make sure that people saw it. The last thing you do, once you choose the desired speed, whichever highest head you want to do, hit set again. Make sure you hit set again. All right, that last set. All right, just because the number's on the screen, it might be flashing. You got to hit that set and make sure it is locked in there. Okay, so very simple to set up, but again, you need to know the highest head the system's going to operate on, and then it will become that variable speed functionality for you. All right, proportional pressure. All right, why do we want proportional pressure? All right, now we have something that is not just an open closed zone valve, but the pressure is going to be proportional on a 50%. All right, increase or decrease. It all depends on which side of the curve you're standing on when you look at it. All right, and it's also going to be valves that never know full open or full close. So again, we have those set curves, all right, that is programmed into the circulator itself. Now, this one is going to be a lot more software built into what's happening here. You choose your highest, again, find your highest head that the system is going to be. Same calculation that we did before. So you're going to have some sort of valves that are opening and closing, but we need to know full case scenario, full flow, highest head. So all of the zones, add up the GPM, find the highest head, that's your maximum point. Now what we have are valves that are closing, or we might have a three-way valve, or we might have two-way valves, but a different layout, and you'll see in a minute on what I'm talking about, where we want the head is going to decrease. All right, as my flow decreases, my head also decreases because I don't need it to work as hard anymore because of the way that maybe a TRV valve is installed in the system. So again, you'll see that sawtooth function, but changing which curve it operates on, but at the same time, starting to use a lot less power. All right, a lot less power as we go down through the system. As before, we were looking at 10 foot ahead as say as our maximum. All right, and it was following this line back and forth. All right, and over here, it might have been operating, 5 curves higher. Now, all of a sudden, in a proportional curve, it's on a lower curve, all right, trying to drop that speed of the circulator. And what we have defaulted into the circulator is a 50% proportion, all right? So if your maximum was, say, 10 foot ahead, your minimum is going to be 5, all right? That's a default in there. We can't change that from the faceplate. In 2 weeks, I'll show you how we can do that, okay? But today's session, we're not gonna be able to get into those details. But default 50% reduction, and it's going to follow that blue line that you see there. All right, now, where do you see applications like this other than see a thermostatic radiator valve, some sort of valve that's slowly opening and slowly closing? We might have two-way valves like this, an extended header. So you might have this main going throughout the entire structure, and then we tee off to our different zones and areas that we have here. And now you can see the pressures are going to be different all over the place. This is an excellent application to do proportional pressure. All right, because whenever a zone is running, this head loss is going to be different for every one of them out there in the system compared to that compact one, when we had that header right next to the circulator itself and then branching out. This one is an excellent application to go with a proportional pressure. So this way, again, the circulator speeds up and down, but is also decreasing the amount of energy being used at the same time, especially if we're looking at this last one out here. Now, each one of these zones could be a totally drastically different head loss, lengthwise and flow and what we have out there. Again, take that, add up the gallonage, find the highest head, which is going to be the header as well as the branch for your pressure drop, and then the return coming all the way back. All right. So this is an excellent application for that proportional pressure mode, as well as this one is. All right. So we're looking at, oh boy. Oh boy, I just forgot the type of piping, John. I did it again.
Reverse return, Dave.
Thank you. Wow. I don't know why I just look at this and it's just not sticking in my head. Reverse return or direct return, right? So this is your reverse return, or I like to call first in, last out. And I'm going to go back a slide so you can see somewhat of the differences. There's not a lot of differences, but there is. All right. Different designs, different layouts. These are both excellent applications for a proportional pressure here. All right, as well as this one here. Now we're going to see where we do see TRVs maybe mounted out on a radiator itself. But again, we have that extended header. Not everything comes back to the mechanical room. We've got a main pipe that goes out, and then we branch off from there. So when you're trying to think about the best application for this circulator, now this one might have this buffer tank or a hydro separator in the middle. So we're going to see the one feeding our system is going to be set up in my proportional pressure, where now I'm going to look at on the right hand side would be set up in a fixed speed mode, because this is again a fixed amount of pipe that we see here. All right, programming here is going to be very, very similar to your constant discharge pressure. Again, you're going to have half-foot increments. All right, but like I said, it's defaulted to a 50% decline. All right, so you choose your highest, your minimum is going to be 50% of that on the foot ahead. All right, half-foot increments. All right, hit the set button. Make sure you choose the right icon. So now we're looking at the one, looks like an arrowhead tied into it here. All right, make sure that light is flashing, hit set. All right, and then change your settings to the half foot, your highest head that you want it to operate at. Hit set again, and you're done. Just make sure you hit that last set. All
Hey,
right.
Dave.
Yes, sir.
We had an interesting question from Ken, who wanted to know, what if we don't know the head? How do we set up constant pressure? And I guess the same can be said of proportional pressure. That's a terrific question. And fortunately, there is a little math formula you can use to estimate the head. The best is to actually calculate it out. But if you wanted to estimate the head, let's say for a constant pressure setting, is you want to measure or estimate as best you can the total length of that run, that piping run, as best you can. It's not an exact science. It's your best estimation. Multiply that number by 1.5 to allow for valves and fittings and things that are in the way. That'll give you what we call a total developed or total equivalent length. And then you multiply that number by 0.04, which is 4 feet of head for every 100 feet of straight, properly sized pipe. And that'll give you an estimated on the high end head loss. At least it'll give you something to work with. It's not a total guess, which is the other alternative. So that would be, to me, the best way to do that, other than actually, getting into some calculations where you can get a more definitive number. That would be, that's a Friday afternoon residential type of setting. In a more commercial setting, you might have other means to do that. Checking pressure differential on the supply and return side would be a great way to do that.
Yep. The other thing that you can do is still going to have to do the math, no matter what.
Yeah.
All right. So the one way John was just showing you was the head loss, how to figure out the head loss. Now, if you're not sure, but you do know what your gallons are, you still need to know the GPM. What is your flow rate going out to the system? All right. What you can do is make sure you program it. You could program this circulator in the fixed speed mode. Choose your RPMs that's closely matched to the gallons per minute you want it to do. All right. What's going to happen is that the circulator is going to come back and rotate, and it is going to give you an estimated foot ahead based upon that gallonage going through the system itself. All right. Now, just make sure that the foot ahead that it gives you is not the maximum of the pump, because obviously it can't read any more than the max. All right. And so it may not be a good idea to drop it in there and say, well, I'm just going to estimate because, well, what if I needed the next size? All right, that it maxed out on the foot ahead that it was doing. It couldn't do any more than max. So you follow me? You know what I'm saying?
Mhm. Yeah, and I
So
think it's important to understand too, auto functions don't do this for you. This is one of
correct.
the big myths about auto anything is that they magically size stuff for you. That's really not the case, and Dave will get into that as well. But don't be seduced by the auto functions.
And right here, that's the perfect lead in, JB. There's the next
It's
slide.
like we've done this before.
So let's take a look at Takeo Adapt, all right, the automatic function of the circulator itself, which is the default mode of the circulator, but very rare are we running into needing to use this Takeo Adapt function. All right, Takeo Adapt is now really what it's doing is it's going to choose your proportional pressure curve. Which one of the proportional pressure curves to operate on. That's really what it's doing. So you got to make sure it has to have that. All right. So in order to choose it, you got to make sure all three of the criteria here are met in order to use it. Otherwise, don't use it. All right. Not used for a lot of systems. If you do systems like I just showed you before in proportional pressure, all right, that's number one. All right. So when do you use Takeo Adapt mode? All right. One, out of the default mode of the circulator, if you don't get into the advanced programming, which we will talk about in part 2, all right, your flow-in head has to fall within a default wedge that we have built in. If your flow-in head does not fall into this wedge at all, it's not going to work for you. Now, will the circulator turn on and will water start moving around? Yes. But if your design was up here, up in this section, okay, when you plot out your pump curve, all right, and it comes through like this, when the circulator is running, and if it doesn't have any sort of proportional valves in it or anything that's changing, it's going to operate right about here. It's going to be underperforming, all right, based upon that design day. And it's not going to do a lot of things. So you got to make sure it's going to fall within this wedge. Number 2, you got to have the piping arrangement matched to it. All right, you need to see like this, even if you have open close, but you're looking at some sort of modulation or three-way valves, or that extended header with two-way valves on the system itself. So the piping has to match. If you have a zone pump system and you leave it in Takeo Adapt, it's not going to learn anything and it may not give you the right flow. Okay, so you got to make sure that's going to be there. And then the last but not least, we're looking at really long run times. All right, almost constant circulation of the circulator itself. So a zone pump or an on-off application is not a really long run time. All right, so we're looking to have that circulator run for an extended amount of time in order for you to choose the Takeo Adapt mode. All right. So, anything? Oh, okay.
Just real quick, and that's true with any manufacturer's auto mode. It's not just ours. That if it's not running continuously, it doesn't really learn. It just, when it stops, it picks up where it left off. So that continuous circulation is an important element of any manufacturer's auto mode. Just want to make sure everybody was pretty clear with that.
Okay. So programming this circulator, all right, this one's going to be real easy. One, if you get it out of the box, it's already going to be set up in that mode. That is the default mode of the circulator, so you're done. All right. However, if it's not, you just hold down the set button and you just hit the up arrow until you hit the A button. The A light is flashing, hit set again, and you're done. All right. So obviously, we're not doing any programming from here. Now, how do I change that wedge that we were talking about? Again, like I said, that's going to be in part 2 next time. So that's what's going to come up there. And that's it. So, but remember one of those things. Hang on a second. All right, I'm going to go back for a second here. All right, and to start talking about when, like John was just saying, when to use Takeo Adapt and what is actually going on inside the circulator itself. For one, it needs to see a change in flow. All right. And it has to see that change in flow over a time period. So the circulator, one, has to be powered up, running, all right, has to be running for an extended amount of time. Then, after it's been running for that extended amount of time, say like 90 minutes, Then it starts to look for changes in flow. If there's been no flow change in 90 minutes, it says, oh, we're good. We're just going to stay here. But if the flow starts to increase, like a valve opening up or a TRV starting to slowly open, now it's seeing that flow change. And it has to see that flow change slowly increasing and or decreasing for another 90 minutes. And it says, okay, let's now start doing some calculations, and let's start either one, speeding up and choosing another curve, because it's doing slow incremental changes. We're not, quick openings and turning on and off again and sending the signal away that it's not operating, not needed any longer. So you need to have those long run times, but we got to see those changes happening. And if we turn it around and take the signal away and say, all right, we're done, all right, it forgets everything. It's not going to keep it in memory, even though this circulator is going to be powered up continuously. All right, the call for heat, and we'll talk about the wiring and programming next time. If the call for heat goes away, yeah, we're just going to start all over again the next time it gets a call. So it doesn't keep that memory and what's happening. It's only taking a look at what's happening at that moment. All right, if that makes any sense to you out there.
Danny sure kind of confirmed that. We installed a 0026E on an extended header with zone valves. The adapt feature works well there. The pump is basically running 24/7. So that continuous circulation is critical to make any of these things work as intended.
Right, right. And the 26E, in case you're not familiar with that, that is the way smaller brother of the VRs here. All right. The 26E is a 26-foot ahead, 44 gallons a minute. All right, these VR circulators. And again, I you know what, I had thought about adding those to this presentation, and then I was looking at the time period. So I know we talked about those in other classes as well. So very similar operation, but different faceplate, doesn't have the same programming on there. So excellent, Danny. Thank you.
We had another good question, request actually. Could you explain again the reason for the pump's amp draw going down when zone valves close? Why does how does the amp draw go down when zone valves close? Because again, I think that, as you explained it, the gut reaction is to think, well, zone valves closed, it's got to work a little harder, so it's going to go up. But why does it go down?
Because of the amount of water available. All right, so the amount of water that you can pump now has just dropped. Let's say if it was only two, dropped in half. All right, if you had two zones that were equal in size, equal in length, the amount of work that it has to do, all of a sudden you got two of them. It's just trying to push as much as it can into each hole. As soon as I lose half of it, the circulator says, well, I can't pump any more than this. This is what I already figured out it needs in this one pipe. All right, you put the two of them together, it just says, all right, let's pump that much. One goes away, what the circulator sees has just cut in half. So it's all about the volume of water that it can do. That's why the amp draw goes down. So it's not trying to take, if we had two zones and each one was doing 20 gallons a minute, we're not going to try to shove 40 gallons a minute through one hole. All right. The circulator is going to say, nope, I'm going to maintain 20 in this hole. So now I only have 20 that I need to pump out, not 40 any longer. I hope that makes sense out there. So that's how we do the calculation with a delta P circulator, pressure differential. It's all about that amp draw and RPMs.
Yeah,
so,
essentially it's figuring out that it doesn't have to do as much work, and it's doing it almost instantaneously.
Yep.
It doesn't have to do as much work. Well, the amp draw is going to go down.
Yeah, it takes probably 5 to 8 seconds or so for this thing to settle out at that point. So it operates really fast at that point. Excellent, everybody.
Terrific, terrific. It's like it acts like a barometric damper on a system, says Eugene. Since I don't know how a barometric damper works, I guess that's fine. Yeah. Oh, that makes sense. That makes a lot of sense.
Right, right. So there's your programming for your Takeo adapt mode. All right. And that'll get you what you need. Again, and now it's in the learning mode, and we'll talk about getting this thing set up and operating and things like that next session. Not the next session, but the next time I will be on board. With that being said, I do want to say thanks, everybody. Greatly appreciate it. We did end a couple of minutes early here. Not too bad. John and I and Jason will stay online as long as you want us to. If you've got any other questions to talk about with this series, circulators, want to use when and where and why. I've also included the catalog sheet for this circulator, as well as the instruction guide for these circulators on how to set it up. I do want to point out next week's session before we go again. Next week, we're switching over to commercial. All right, so now you're going to get Rich and Brett and Tony involved, and they are doing HVAC hydronic balancing. All right, so that's the June 3rd session. So make sure you get onto the website if you haven't registered for it just yet. All right, come to next Tuesday's class. I'm going to assume most of you here are already signed up for it, because
774, man.
we saw a lot of people wanting to join this class next week. So tonight, today's class, we had about 250 of you register for this class, and next week I saw 770 registered. So sounds like a topic that people want to know about. So very, very interesting. So it sounds like I need to go.
I'd say so.
They must be giving something away, all right, in order to get 770 people registered for this class.
Hey, it's all balancing act. Boom.
Hey, that's a good one.
That was quick, huh? That was quick.
Hey.
Boy, just jammed on that one. So we'll stay online as long as you got some questions out there, everybody. Let's see here. Anything else? Now I can finally see the questions since I'm not talking any longer.
I think we got them all so far, but you guys have any last minute questions? Now's the time to type them on in, and we will be happy to discuss with you. Let's see, we've got, here we go. No, just about a lot of thank yous. Okay, well, cool. Well, thank you guys. We do appreciate the gift of your time on this last Tuesday in May. Where has the year gone, man? Where has the year gone?
Yeah, that is nuts. That is nuts already. So thanks everybody. Thanks for attending another Takeo Tuesday with us. This is a fun class. This is I know you might look at the three of us as the residential guys in here, and this product here is kind of like what we call that crossover between some of the commercial big pumps that Rich and Brett and Tony get involved with, and then this gets always down to the small pumps that we get to play with on a regular basis as well. But hey, there are applications where I've used these circulators in some snow melts, some heating systems, geothermal out there. So looking at some of these bigger projects, and still keeping the ECM out there. All right, remember everybody, we've got less than 3 years now.
Yeah, less than 3 years.
Less than 3 years. Less than 3 years. The standard AC circulator choices will not be available. Everything will be ECM.
Check that 3 years from tomorrow.
Ooh, that's right. The 28th.
No, 22nd.
Is it the 22nd? I always thought it was the
28. 2028. Yep.
Okay, 20. Okay, it's the 22nd. So it's a little less than 3 years.
A little less than 3. Yes. Yep. So 3 days less than 3 years worth.
There you go. That works for me.
Well, 4 days. 4 days. Yeah. 4 days.
Actually, technically 5, Dave, but we won't hold you to it with the.
Well, one of those days is going to be a weekend, so we don't count that. I was still thinking today was the 25th, actually. So yeah.
That's all right. You're a couple days behind. That's all right.
Yeah.
That's all right.
That's when I realized I had to put this class together. So thanks, everybody. Just so you know, for those of you out there as well, Takeo After Dark still running. All right.
Tomorrow night, baby.
Tomorrow night, 7 p.m. All right. On domestic hot water indirect tank sizing, as well as circulators. And why would you want to use a mixing valve? So that's going to be Takeo After Dark tomorrow night, Wednesday, 7 p.m. Eastern. Or for Jason, it's Takeo in the afternoon.
Yeah, Takeo after lunch.
Yeah.
Takeo after lunch.
So, thanks, everybody. Thanks for joining us.
Dave.
Greatly appreciate it. Look forward to seeing you tomorrow night or at least 2 weeks' time.
Awesome,
So long,
Dave.
everybody.
Have a great one.